For this project, our group explored various deep learning methods to apply style transfer to music. The core question is this: can we take the concept of image style transfer and apply it to music? Audio can be extracted via the short-term Fourier transform into these 2D representations we call spectrograms. In these example spectrograms, we can see country music, disco, jazz, metal, and blues. We can see a sort of style pertaining to each genre spectrogram. We want to see if we can capture this style and apply it to the content of another audio input spectrogram to create an all-new audio sample which contains the content and style of the respective inputs. The intuition for our project comes from a number of papers exploring music, style, and translation. Noam Moore's A Universal Music Translation Network lays out an unsupervised learning method for translating music across instruments, genres, and styles. Yolanol's project, which more closely resembles ours and is where we derive inspiration from, performs texture synthesis between STFTs of different audio files. We apply the intuition behind unpaired image-to-image translation using cycle-consistent adversarial networks to design the GAN model in our project by training two generators that perform style transfer in opposite directions. Our project ended up being a two-pronged approach to exploring music style with deep learning, with plans to unite them. The main focus of this project was how to capture content and style respectively from two different audio inputs and generate an output that carries the content of the content input and the style of the style input. Our baseline model was a CNN using Graham matrix to calculate style, and second approach was a recurrent model using RNN and bi-LSTM, and the third approach a GAN. In order to obtain a more measurable benchmark of how well our generating models were at producing the audio of the desired style, we also need to design classifiers to tell us what genre the input is. We tried two approaches, both based on different features of the audio input. In our baseline approach, we implement a CNN that learns how to manipulate an input to make it into the desired style. The loss is computed by computing the mean squared loss between the Graham matrix output of the CNN output and the Graham matrix of the style input. Our second approach was to use recurrent networks. Since audio is a time series data, we thought RNN should be a better model for analyzing and generating audio because they take into account the output from the previous step. The RNN we trained is composed of a single RNN layer fed into a linear layer, which produced the output. Like in the baseline, the Graham matrix of the output is compared against the Graham matrix of the style input. On using a deeper network, the model was not able to pick up the content of the music, and so a shallow network was selected. However, with the RNN, we encounter the problem of vanishing gradient and forgetting, so we try to remedy the issue with a bi-LSTM network. This model has a single bi-LSTM recurrent layer whose outputs feed into a linear layer that produces the output. Again, the Graham matrix of the output is compared against the Graham matrix of the style input using mean squared error loss. For the third approach, the GAN, we take inspiration from cycle GAN and train two generators, one transferring style A to B and the other from style B to A. We also train a discriminator for each generator, one determining whether the input is of style A, and the other determining whether inputs are of style B. On a more detailed level, the generator computes three losses. We pass the genre A input through the A to B generator and obtain input A stylized to genre B, which we can call fake B. The first of the three losses is our identity loss. If we pass an input of genre A through the A to B generator, then we would expect that the input does not change at all. The second of the three losses is our recovery loss. If we pass the fake B through the B to A generator, then we would expect the recovered output of the genre A to be the same as the input A. The last loss is the traditional generator discriminator loss, where we feed the fake B to B discriminator. We want to fool the discriminator, so we feed the discriminator output to a mean squared error loss with a vector of 1s as to represent real. These three losses are weighted and added together produce a total loss of the generator. We do this also in the mirror direction, where we produce fake A and test generator B to A with the discriminator A. The discriminator is trained in the same way that it is for a traditional GAN. We add the losses for mispredicting true genre B inputs and for being tricked by fake genre B inputs. As we tested different models over the course of this project, we observed that the one that performed best was the bi-LSTM. The reason for this is likely the fact that recurrent networks handle inputs as time series, and as we know in music, the next node is dependent on the previous one, and has various different characteristics as per the genre of the music. The bi-LSTM performed better than the RNN, likely because music also does have long-term relationships over the course of a song, and a bi-LSTM is more capable of capturing that information. The CNN and GAN, on the other hand, are more geared for visual images in which object relationships are close to one another spatially, and so it had trouble capturing musical relationships such as harmonics and beats. We run the model on the same inputs to see the difference in results. We transfer the jazz style onto a classical content. Here's what the jazz sounds like on its own. And here's what the classical sounds like on its own. The baseline produces the following output. The GAN produces the following output. The RNN produces the following. The bi-LSTM produces the following. As we can see, all results are rather noisy, but we can perceive a slight transfer of the upbeat, swingy jazz style onto the classical music. The most effective model is one designed to work with time series data, and that is capable of maintaining relationships over distance, whether across differing frequencies or across time. The most important issue to address in further work is how to either shape the noise into style or content perceptible by humans, or to eliminate it. We think that one way would be to design a model that strips the high-level style away from the audio input and leaves just a pure representation of the raw content, the lower-level features. When manipulating the high-level features of this isolated content, hopefully we can eliminate some of the noises that we are getting with our current approaches. Deeper knowledge of signal processing and audio perception will be necessary to design more refined models once this noise is managed.